Hey everyone, welcome to Instrumentation videos. In this video, we are going to learn about dimensions and dimensional analysis. Dimensional analysis is a very important tool or concept in physics. It is a key topic to know before starting any course on physics, chemistry, mechanics, or basically any course that's an application of science. So, every science and engineering student should know this topic very well. Before watching this video, you should be familiar with unit analysis and understand the difference between fundamental and derived units. I have already made a video on that, and if you need the link to that video, it is available in the description. Let's start our lecture now. So, what is dimension? Dimensions and units are closely related but different concepts. We use units to measure physical quantities. On the other hand, dimension of a physical quantity is independent of the particular quantity chosen. For example, we can use centimeter, meter, or kilometer to measure length. Here, centimeter, meter, and kilometers are the unit of length, that is, we call them units, and this length is what we call dimension. Okay, there are 7 fundamental dimensions, and they are length, mass, time, current, temperature, amount of substance, and luminous intensity. The symbols associated with these dimensions are these. Now all other dimensions are obtained by taking combinations or products of these 7 fundamental dimensions and are called derived dimensions. For example, we know that speed is equal to distance by time. Therefore, the dimension of speed, by the way, we use square brackets around the symbol for a physical quantity to represent the dimension of that quantity. For example, if r is the radius of a cylinder, and h is the height of the cylinder, then we write r within square brackets equal to L and h within square brackets equal to L to indicate that the dimensions of radius and height are both those of length L. Okay, so coming back to our speed, we have speed is equal to distance, and the dimension of distance is L, by time, and the dimension of time is t, is equal to L t raised to minus 1, which is L t raised to minus 1. So the dimension of speed is L t raised to minus 1. Similarly, we can find the dimension of force. We know that force is equal to mass into acceleration, and this is equal to mass into velocity by time, because acceleration is velocity by time, and we can again write velocity is equal to displacement by time. Therefore, this is displacement by time, and this can be written as mass into displacement by time square. And we know that the dimension of mass is m, dimension of displacement is L, and dimension of time is t, and we have t square, so here also t square, and this can be written as m raised to 1, L raised to 1, and t raised to minus 2, which is dimension m raised to 1, L raised to 1, t raised to minus 2. So this is the dimension of force. Now I want all of you to pause the video and try to find the dimension of energy. Okay, so the dimension of energy is m raised to 1, L square, t raised to minus 2. To find this, remember that energy is equal to force into displacement. In general, the dimension of any physical quantity can be written as L raised to A, M raised to B, T raised to C, I raised to D, theta raised to E, N raised to F, and J raised to G for some powers of A, B, C, D, E, F, and G. We can write the dimension of length in this form with A is equal to 1 and all remaining 6 powers set equal to 0. That is, dimension of length is equal to L raised to 1, M raised to 0, T raised to 0, I raised to 0, theta raised to 0, N raised to 0, and J raised to 0. So, we can define dimension as the power or exponents raised to the base quantities of the unit. Now, any quantity with a dimension that can be written so that all 7 powers are 0, that is L raised to 0, M raised to 0, T raised to 0, I raised to 0, theta raised to 0, N raised to 0, and J raised to 0 is called a dimensionless quantity. Dimensionless quantity. Sometimes they are also called quantities of dimension 1 because anything raised to 0 power is 1, right? So this is also called quantities of dimension 1. And dimensionless quantities are also called pure numbers. Pure numbers. Okay, now there are some properties of dimension. If you have an equation, then all the terms in the equation must have same dimension. For example, in y is equal to mx plus c, the dimension of y should be equal to the dimension of mx, which should be equal to the dimension of c. That is, any mathematical equation relating physical quantities must be dimensionally consistent. Now the second property is that dimensions must obey rules of algebra. As you have already seen, multiplying two terms multiply their dimensions also. Now coming to the third property, many standard functions like exponential, logarithms, or trigonometric functions cannot have input variables that have dimensions. I mean, what would e raised to 1 kg even mean? Like, what units could it possibly have? So, standard mathematical functions such as trigonometric functions, logarithms, or exponential functions require pure numbers as input and pure numbers as output. Now coming to the applications, the most important application of dimensions is dimensional analysis. Using dimensional analysis, we can check whether an equation is dimensionally consistent. For instance, we know the famous equation E is equal to mc square. That is, energy is equal to mass into square of speed of light. But how can we be sure that the RHS of this equation is representing energy only? For that, we can use the dimensional analysis. We have already seen that the dimension of energy is m raised to 1 L square T raised to minus 2. Therefore, the dimension on LHS of this expression is m raised to 1 L square T raised to minus 2. Now let us check the dimension of expression on RHS. We have mass, so we have m, then we have c, which is speed of light, and the dimension of speed is L T raised to minus 1. So here we have c square, therefore L T raised to minus 1 square, which is m L square T raised to minus 2. Therefore, the dimension of expression on LHS of this equation is m raised to 1 L square T raised to minus 2, and similarly the dimension of expression on RHS of this equation is m raised to 1 L square T raised to minus 2. You can see that dimensions are same on both sides of this equation. Therefore, this equation is dimensionally valid. However, please note that just because an equation is dimensionally valid does not mean it is a correct statement of physical law. That is, just because an equation is dimensionally valid does not imply that it is correct physical law. Okay, for example, consider the equation S is equal to ut plus at square, where S is displacement, u is velocity, and a is acceleration. The dimension of S is L. The dimension of ut is L t raised to minus 1 into t, and therefore this is also L, and dimension of at square is also L. So you can see that this equation is dimensionally valid. But we know that this equation is wrong. The correct equation also have a half term present here, right? So we can see that although this equation was dimensionally correct, it was physically wrong. So this is a limitation of dimensional analysis. That is, we never get any information about the constants in the equation. Now the second application is to derive the relationship between physical quantities. For this, let us take the classic example of a simple pendulum. Our objective is to find the time period of the pendulum. The first step is to identify all independent physical variables of the pendulum and dimensional fundamental constants of the system. That is, to identify all independent physical variables and dimensional fundamental constants of the system. This is the most difficult part. Okay, so here let us take the length of string of pendulum. So we have L, which is length of string. Then let us take mass of the bob of pendulum, M, mass of bob. Now we also know that the swinging of pendulum depends on the acceleration due to gravity. So let us take G, which is acceleration due to gravity. And finally we take T, which is time period of pendulum. Okay, so we believe that we have considered all independent physical variables and dimensional fundamental constants of the pendulum system. Now the dimension of length of string is L, dimension of mass is M, dimension of acceleration due to gravity is L t raised to minus 2, and dimension of time period is T. Now this time period T of pendulum is dependent on length of string. But we don't know how it is dependent. Maybe proportional or maybe inversely proportional. So let us say that time period T is proportional to L raised to A. If this A is positive, it means that it is directly proportional. And if this A is negative, it means that it is inversely proportional. Alright. Next, time period is dependent on M raised to B, that is mass raised to B. And time period is dependent on G raised to C. Now combining these three equations, that is combining equation 1, 2 and 3, we get T is directly proportional to L raised to A, M raised to B and G raised to C. To remove the proportionality, let us also put a constant. T is equal to K, L raised to A, M raised to B and G raised to C. Now let us put in the dimensions of each variable in the equation. We know that the dimension of time period is T. Sorry, this is small t because we have used small t over here. Here also small t is equal to We can ignore k as it is a dimensionless quantity, and we have L raised to A, and the dimension of length of string is L. So L raised to A, M raised to B, and dimension of G is L T raised to minus 2, and this is raised to C. We can again write this as L raised to 0, M raised to 0, T raised to 1 is equal to L raised to A plus C, because we know that x raised to A into x raised to B is x raised to A plus B. Therefore, L raised to A plus C, and we have M raised to B and T raised to minus 2C, because we know that x raised to A raised to B is x raised to AB. Equating the powers of L, M and T on both sides, we have A plus C equal to 0, that is A plus C equal to 0, B is equal to 0, and minus 2C equal to 1. So minus 2C equal to 1. From here we can write C is equal to minus half, and plugging this C in here gives us A is equal to plus half, and we have B is equal to 0. Plugging these values of A, B and C in this equation gives us time period is equal to K, L raised to A, which is half, M raised to B, and B is 0, therefore M raised to 0, and we have G raised to C, which is minus half. This gives us G is equal to K root L by G. So this is the equation for time period of a simple pendulum. As we have already discussed, we cannot obtain the value of constant K using dimensional analysis. One way to find the value of K is using experimental analysis, where we can determine the constant K by measuring the length of string, timing the period of oscillation, and using the fact that G is equal to 9.8 meter per second square. Once we know these values, we can use K is equal to T root G by L and find the value of K. Scientists have already done this and have found that K is equal to 2 pi. Therefore, the final equation for time period of a pendulum is T is equal to 2 pi root L by G. Okay, now before we sum up, one further point that needs to be mentioned is the effect of the operations of calculus on dimensions. We will see what happens to the dimensions when we take the derivative of one physical quantity with respect to another, or integrate a physical quantity over another. The derivative of a function is just the slope of the line tangent to its graph, and we know that slopes are ratios. For instance, if we take the derivative of velocity with respect to time, the dimension of the resultant quantity, that is acceleration, is simply the ratio of dimension of v over dimension of t, which is L t raised to minus 1, and we know that this is the dimension of acceleration. Similarly, since integrals are just sum of products, the dimension of integral of v over t is simply the dimension of v times the dimension of t, which is L t raised to minus 1 into t, which is L. And we know that integral v dt is displacement, and this is the dimension of displacement. Okay, so to sum up, the dimension of a physical quantity is just an expression of the basic quantities from which it is derived. Also, all equations expressing physical laws or principles must be dimensionally consistent. This fact can be used as a way to check whether claimed relationship between physical quantities are possible and even to derive new physical laws. That's all for this lecture. If you found the video useful, please like the video and also subscribe the channel. If you have any doubts, drop them in the comments so that either me or some other viewer can help you. In the next video, we will start our discussion on characteristics of measurement. Thanks for watching and have a nice day.